The BCS theory of superconductivity ties superconductivity with the condensation of electrons into Cooper pairs. The BCS system is described by this Hamiltonian, which is further simplified by using Anderson's pseudo-spin representation. Here, epsilon j is the single particle energy dispersion and chi is the pairing interaction, which is related to the BCS pairing gap. Studies on the pairing dynamics of the BCS system have shown that subjecting it to a quench causes the system to evolve into three distinct dynamical phases described by the order parameter, the pairing gap. Phase 1 shows a decay of the order parameter to 0, Phase 2 shows transient oscillations, and Phase 3 shows persistent oscillations. Periodic driving of systems can produce fascinating behaviors. As for superconducting states, studies show various effects including parametric resonances, Rabi-Higgs oscillations, and locate time crystal phases when a periodic pairing interaction is utilized. It is then tempting to ask, what if we apply a periodic drive to the oscillatory dynamical phases? Besides, subjecting an oscillatory system which has its own natural frequency to an external periodic drive is something entirely interesting on its own, as synchronous fireflies demonstrate. When a synchronous firefly is exposed to a flashing artificial light stimulus with constant frequency, they discovered that for reduced frequencies close to the firefly's natural frequency, the firefly was able to match its beating with the external stimulus. This phenomenon is called entrainment. Inspired by fireflies, further wonder if we can affect the oscillatory dynamical phases frequencies by applying a periodic drive. Is entrainment possible here? This is what we investigated in this thesis, where we sought numerically the fate of the oscillatory dynamical phases of the Bardeen-Cooper-Schrieffer Superconductor once they are subjected to a periodic pair interaction, using a Cavity-QED platform designed to simulate the dynamical phases. We discovered that for the majority of test frequencies and amplitudes, the dynamical phases demonstrated chaotic responses with sparse frequency-amplitude pairs that demonstrated minor signs of entrainment. We also observed an unyielding behavior of phase 3 against high-frequency driving. More information will be discussed in this thesis defense. If you want to hear more, I guess I'll see you there.